Every 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
Hello everyone, welcome to ASRG's and PCAutomotive's webinar about the road to the roads. My name is Janos Kovacs and I work as a lead cybersecurity consultant at PCAutomotive, and I also have the honor to be a guest lecturer and co-author of the Cybersecurity of the Embedded System course at University of Óbuda, Hungary, Budapest, and I'm also proud to be a husband and father of 2 at Kovacs family. My hobbies are among cybersecurity and vehicles, of course, the reading of fantasy novels, painting miniatures, Warhammer 40k rules, fishing, and working out. Let me tell you a story about a battery management sensor, BMS, containing a nice TI-TMS microcontroller with JTAG debug interface and internal flash, which implements LIN bus communication, and on top of it, bootstrap loader interface, and basically implementing as its primary function an analog voltage measurement via its shunt resistor, measuring the current running towards the battery ground connector. In this picture, here is an example for the sensor, which I found at eBay. What are the use cases of such BMS? First, basically measurement of the battery voltage to provide the feedback about the charge level and the battery health. Okay, this is very nice. And what is it used for? Basically, the primary goal is to decide whether the vehicle can trigger the auto start and auto stop feature of the engine to preserve the fuel consumption. And of course, it can use it for planned and in advance planned maintenance to be able to decide whether the battery is facing in the end of its life cycle. And what can happen if we start to abuse these features? What can happen? This is the primary and the most interesting question regarding product cybersecurity, I can tell. First, if we start to falsify by spoofing and tampering the BMS signal, then we can say that, for example, the battery voltage is completely okay. Let's just continue stopping the engine. Let's just continue forcing the battery to load it with the ignition cycles over and over again. And if we are keen enough to doing so, then the battery will eventually go dead. And also, if there is any other feature relying on the battery voltage, then we might able to cause a denial service for all of them, because even just if we, for example, trigger false need for battery change, or just we create a denial of service about the need, the communication of the need for battery change, then the end users, the road users, will face some inconvenient circumstances. Let's just think about the battery management sensor. Here it is now in this picture. But ever you wonder how did it get here? It all started at the semiconductor factory when the MCU peripherals were created on the silicon wafer, implementing basically the foundation stone of the microcontroller unit. Then they used the production process to set up the appropriate default microcontroller unit configuration, including the enabling of the security peripherals, for example, the JTAG debug port, and enabling or disabling the memory protections, which might affect the accessibility of the internal content of the microcontroller unit. Then the boot-ROM firmware is written to the MCU to a one-time programmable area. And then the default boot sequence is set for the MCU. Then the MCU will know what partition to boot up by default. And of course, this information might be modified later, but for first, everything gets where it's supposed to be in the silicon wafer, and then it just get a proper pinout, and it get the proper resin package. After that, the microcontrollers are shipped to an electrical control unit facility, an electrical control unit manufacturing facility. In fact, a large electronic factory. And then this factory manufactures the system for the request of one of the tier ones, and the firmware is flashed onto the microcontroller unit to implement the system functionality. In this case, the battery measurement and the communication of the measured and calculated values belonging to the battery. Then the sensor calibration data is adjusted in the microcontroller because the sensor calibration data is just simply relies on the imprecision of the sensor, in this case the shunt resistor, because non-shunt resistor is created to be equal, and the resistance is happen to be varying by piece, and this can be, in this case, compensated with, for example, setting up an offset for this measurement. After that, manufacturing logs might be saved onto the product to provide an evidence that the due care and the due diligence of the manufacturing process was carried out by the manufacturing organization. And after that, the supplier secrets, key, passwords, which are necessary or might be necessary for maintenance, and the later configuration of the product are flashed onto the MCU, and the security configuration can and should, I should say, be modified before shipping the MCU to the customer. About the security configurations, we will have some talk later. Financially, the system gets integrated into a vehicle by a well-known global OEM. That's nice. The logs can be put in the retention on a server to preserve for later use, to preserve for provide the evidence that the chain of custody was intact, and they might be deleted from the MCU to provide space for additional applications or additional data. The further calibration data, for example, the adjusting of the ECU to the type of the battery used can be set. And the certain set of crypto data, for example, passwords, keys, just like the ones I told you before, could be and should be replaced to assure that the control on the cybersecurity functions remains on the OEM side, and the OEM will be the sole organization who can manipulate the behavior of the piece of component later. and the vehicle data is set to bound the component to the vehicle ecosystem. For example, the vehicle identification number is set and the engine identification number is set and so on. And this way, the BMS ECU will be an integrated part and an integral part of the vehicle ecosystem. Okay, what have we seen so far? First, the microcontroller unit was manufactured in a semiconductor factory in China. Then the MCU was shipped to an Indonesian electrical device factory to create an ECU, and then this ECU was shipped back to China to being stored in a center of logistics. After that, eventually the system was then shipped to Japan to make a vehicle, and finally the vehicle was then shipped to other parts of the world wherever they needed, and it also can get further customization in the dealership garage. About cybersecurity perspective, what might be the key takeaway of this information we just learned? The product manufacturing puts the cybersecurity of the product at risk. About confidentiality, confidential data is accessed and is necessary to be accessed and managed during the production by human and technical actors. What do I think about here? Symmetric keys, password, the intellectual property of the organization, because somebody just happened to develop these features and happened to develop these products, and it was a certain investment of efforts to then provide business value later when selling it to the end user, and it should be protected as well. There might be other crypto material handled, used for the security and the further operation of the system. For example, the unique identification number of the microcontroller unit or the electrical control unit. There is the availability aspect of the data, of course, because there is a lot of data generated. For example, the logs I told you a lot, and this crypto material I mentioned before, which, if lost, can cause the serious issue when the organization needs to provide evidence of due care and due diligence during the whole product lifecycle, including, of course, the product manufacturing. And the integrity of the data is also a central aspect of the vehicle industry. The content of the ECU gets modified step by step during the supply chain. This is basically, when the ECU is out, the nightmare of the organizations, that the contents get modified by unauthorized actors. And think about it, that when we have the ECU being manufactured in separate locations, often separate locations and separate organizations than the manufacturers and the vendors, then is basically outside of our reach, outside of our control. And these manufacturers might outsource these activities, but still they are or they can be held liable in case of any violation of the product integrity related cybersecurity goals happens. So considering that the core of these activities are the manipulation of the product content, then it is something that should be taken care about. Like the electronic components can be modified, the software code can be compromised, the configuration data can be compromised, and of course the key material as well, all of them influencing heavily the end behavior of the product. What is about the confidentiality of the product? The access policies of confidential data can be difficult to be maintained at the assembly lines, because there are multiple access points to the content of the data, the content of the ECUs. There are many assembly phases that needs the data for fulfillment of their objectives, because one of these points might be flashing a certain area of the microcontroller, and the other would need to get the access of the microcontroller data, for example, being able to calculate for it just like the offset value. And for getting this access, some entity can get further access as well, and that can be abused, for example, to reach the intellectual property or learning crypto material. After that, the distributed access itself, that manufacturing, in fact, is geologically and organizationally distributed, makes it possible for entities outside of the organization to get the access to this data, which also can violate the confidentiality of both the intellectual property and the crypto material. So these several threats may target distributed confidential information for such broad audience by, for example, stealing the data carrier containing this information, copy the data from the carrier, or using a data breach of the system to get this information. And what might be the best practices to handle this kind of security considerations, security concerns? The best practices here are listed. Starts, of course, with some administrative control, like the non-disclosure agreement, the NDA for the secret data. It should be done inside of the organizations with the employees and outside of the organizations with the supplier. With this, of course, the complete risk is not taken care of, but at least legal evidence is there in our hand, and of course, we have means to do some counteraction in case we detect a breach. We should use the end-to-end encryption for the secret data, both inside and outside of the organization, to prevent the eavesdropping of the communication lines for getting the secrets we want to protect. We shall apply the principles of need to know and least privilege. We should only distribute the information to the entities who certainly need it and avoid sending any information unnecessary for their operation. And with this way, we can limit the amount of data in case of a breach. There is also another consideration and security control, that we should use temporary data that shall be finalized in-house. For example, the secret keys. This way, even if one of our suppliers get a data breach, then that data breach won't have any effect to the crypto materials we use inside our product. And also, as always, we should disable the backdoors for the product before shipment. This way, if anyone malicious actor will get the access to the product, then they won't be able, hopefully, to get the data via the abuse of the debug interfaces. Of course, about the confidentiality, we haven't taken care of everything we can worry about the product cybersecurity. The integrity of the product data is important both for the data received by the organization and also the data sent by the organization. For the data received by the organization, the first we should ensure is the chain of custody. We should make sure that our suppliers seal the backdoors before shipment to prevent the unauthorized access also to the product data. And also we should check the data for unauthorized modification. We should make sure that we get the information in the same form as our suppliers send it to us. And of course, we should make sure that we also seal the backdoors for our product we ship to our customers. And we also ensure that the appropriate content is being shipped. We also have assurance steps checking that what do we ship with the ECUs, within the ECUs, and within the work packages we meant to provide. Here is some practical example for protecting the integrity of the product data and ensuring that the chain of custody is unharmed. The first and the best practice we should recommend is the usage of PKI for digitally signing the content of the ECUs before shipment. Our supplier should have an appropriately managed private and public key pair, or even better, a signing certificate. And this signing certificate should be used by them to sign the memory content of the ECU and attach the digital signature next to the memory content in the ECU memory area. And of course, the signing certificate, the public side of it, should also be attached to the package. And when we receive, it is pretty straightforward anyways, when we received the ECU, then we can easily use the signing certificate to check that the memory content was unharmed after the shipment of the goods. If it is not possible somehow, for example, the production process is already settled down and we should be able only to request our supplier to use this implementation of PKI-based cybersecurity control only after pricey, expensive change requests, then we might rely on making them requesting hash about the memory content of the ECU, and this hash could be out of band sent to us and on our inside our perimeter after the reception of the products. We are also able to do the hash according to the memory content, and we should be able also to cross-check it with the hash received. And if the two values happen to be the same, then we can say that it is very likely that unless someone hacked their, I don't know, out-of-band hash sending method or the PKI management, then the data is in the same form as they shipped it us. And also the availability of the product data. The production, as I said, creates data that might be crucial for business continuity aspect of the organization. These are snapshots, fingerprints, test results, which are or can be important evidence for us that we are compliant to the standards and regulations we must comply with, and even they might be important for some forensic analysis, of course. So we should preserve this data until the time we need it. The availability aspect of the production data therefore should be also revised carefully, and data security best practices general to the information technology and the ISMS should be kept in mind and leveraged to make ourselves able to access the data until we need this. What does the ISO say, on the other hand, of the cybersecurity of the assembly line, more precisely the production? First, it says in the chapter 5 that the cybersecurity management system for the production processes should be established in order to support the activities of chapter or clause 12. I must say that this is an OT security topic, and this should be addressed not solely by the product cybersecurity entities inside the organization, but a close coordination between different stakeholders of the organization should be initiated, because both politically and both economically and both organization management-wise, these topics can be crucial for several stakeholders. And when we taking care of cybersecurity issues regarding to the product, we should be, of course, consider the other aspects of the other stakeholders to keep the business operational. In clause 10, the standard requires us that we should be able to set up the procedures to ensure that the cybersecurity after the development of the components is specified when it is applicable. It is basically saying us to set up a set of requirements and set up the post-development cybersecurity activities, including the production level controls. And there should be specified procedures for the correct integration and the initialization of the cybersecurity controls, as well as maintaining the cybersecurity throughout production. I think the hints we provided in the previous slides gave some ideas for the covering of this area. And what is the outcome? What should be the outcome of these activities? At this level, at least, there should be requirements for post-development specifying the needs to keeping the product secure in the whole life cycle after the development, including the production. In Chapter 12, the ISO 21434 requires us that we should be able to set up a production control plan which applies to the cybersecurity requirements or applies the cybersecurity requirements for post-development. And basically, this production control plan should be included or can be included as part of the overall production plan, or it can be, of course, a completely separate document. And this production control plan shall include the sequence of the steps that apply the cybersecurity requirements for post-development, the production tools and the equipments, and the cybersecurity controls to prevent the unauthorized alteration during production, and the methods to confirm that the cybersecurity requirements for post-development are met. And what does the ISO 21434 says after? Is generous as always. The production control plan shall be implemented. So we should be able to set up that what do we plan to do, and then when we set up this plan, then we should implement this plan. Simple as that, right? What is the control plan then? Just summarizing this topic. In the lower level is the tool chain and the equipment. We should be able to tell that what do we leverage during the production, what is the software and what is the hardware tool chain, and what equipment do we use. And we should keep an asset management database, an asset inventory on these for being able to tell that, for example, if there is any vulnerability discovered for this tool chain that could be harmed while harming also the product cybersecurity, because in this case, these exploits can have a direct effect on the overall end product cybersecurity as well, which in the end affects the security and the safety of our everyday life. And if we know that what do we use, what is inside our perimeters, then we should know the steps, the sequence of the steps that we want to apply, that we plan to apply during the manufacturing of the product, because these are the sequence of the steps that the cybersecurity requirement should be applied on. And after all, in the end, we need to know that what should be the assurance steps that we need to do to assure that the cybersecurity of the product is unharmed in the end of the production line. If we manage to do this, then we can say that we managed to implement, or at least we managed to be able to define the cybersecurity controls, both in terms of OT, the IT, and the product cybersecurity. And with this approach, we are able to say that we managed to harden the production sequence as it is needed by either the regulation or by either the common sense. And what can PCAutomotive help to the organization to overcome these challenges manifested by the production and the supply chain? Of course, PCAutomotive can provide cybersecurity consultation for the production as well, which has two dimensions. The first dimension is compliance consultancy. The compliance consultancy is for meeting the requirements of the regulation 155 and even 156, of course, just as well as meeting with the standards belonging to the cybersecurity and the software update management. And these services contain the provision of the document templates that help the organization to start with, and of course, it contains the process development activities as well, which needs to meet these requirements. On the other hand, PCAutomotive is eager to have technology consultancy as well, which contains a 5-dimensional data, which is unique on the market, I should say, because it includes the production level and the production dimension as well, therefore providing a way for making strong arguments of meeting the cybersecurity goals and provide strong arguments of needs meeting the cybersecurity goals. And of course, technology consultancy involves production control planning as well. Any questions?